Now, I did this a little bit earlier, and so what I'd like to do now is set this aside. We can come back to it later, but set this aside and show you how we calculate RFs, or retention factors, for these compounds. So let's do that. Again, I did this experiment a little bit earlier, and here we have the stationary phase with the two substrates, or the two components of the substrate, pretty well separated. And they streaked really bad, so this is not an ideal case. We would probably spend some time trying to optimize the mobile phase so that we got a dot moving up the paper that was about the same size as the dot we originally spotted, as opposed to something that's really streaky like this. But in any case, we can estimate how far the particular spot moved by just taking the middle of the range of the spot. So let's say that blue moved that far and red moved that far. And then what we do is we measure how far the spot moved relative to the baseline. So for instance, red moved 38 millimeters. So red moved 38 millimeters. And blue moved 55. And then the solvent moved all the way up to the top of the plate, and that's 67. Okay, so we define RF, and actually I think it's little r, is equal to the distance that one of our components moved over the distance that the solvent moved. Which is equal to, for red, (38 divided by 67), 0.57, and for blue, 0.82. Okay, now you can ask, why do they separate? Why do red and blue separate? And the answer is the molecules that make up the red dye and the blue dye have different polarities. And what we're witnessing is a competition between the affinity of the dye for the stationary phase, which is the piece of paper, and the mobile phase, which is the water. Water is very polar. The stationary phase, the piece of paper, is actually also polar as well. And depending on sort of how well the dye, particular dye, sticks to the paper versus wanting to move along with the water determines the fact that we get different RFs for these two compounds. Okay, well, let's go back to our original chromatogram here. And it's tipped over, but we can straighten it out. And it looks like our channel on the right has actually straightened itself out. And you can see that they're well on their way to being entirely separated. It looks very much like the chromatogram that I ran earlier. And again, this is an example of thin layer chromatography, which is used to separate these two food coloring dyes from purple Kool-Aid, to show you that there's no such thing as purple. Well, maybe not no such thing, but in this case, it isn't that there is food coloring that's colored purple here, but rather a mixture of blue and red.